So, welcome back after the break. Now we leave the skeletons and go back more or less to looking at the small round items again. And what you have seen in the component labeling before is that often you have clusters of things that you obviously with your eyes see that they shouldn't belong together. And this is where we can come in with the so-called watershed algorithm, and I describe why it's called like this. But in principle, what it does, it looks at the shape of the structures to find the objects. And the main information that is used is mostly the distance map. And that's is a very useful information. But let's see what we can do. It's a very popular algorithm, and it's used in many applications. In particular, when you have small touching objects, and even some Kaggle winner, he said something about, he used this and that algorithm and so on. And in the end, he used Watershed and Morphology to clean up the space. So let's go back to our cell images, which we have seen so much before already. And we were able until now to be to take the color image, make it into grayscale, segment it. We also did an attempt on labeling, but when we looked at what was labeled and what we got and what we would expect from this picture, it doesn't really look like it. So you can see this example here, that there is a lot of small cells. So these clearly make sense. Actually, that one looks like some wrong coloring, but I believe these are two different objects actually. So this is what we would like to have, but with the component labeling, we would just get a lot of large blobs. So let's try what the component labeling is doing. We have the grayscale image, which we segment and get the black and white. And when you apply the component labeling, you get one block here and one block here. That is what the algorithm is told to do. The ground truth, however, says that it should look like this, that we have actually 4 objects in the image. And that's far away from what we really have. So what we can do now is to look into something called the watershed, and it actually in principle is when you explain this algorithm, it's the analogy to a landscape. So if you have a landscape like the one on the screen now, and put a drop of water in this landscape, this drop will, depending on where you are, if you're standing up on the ridge, nothing happens. But as soon as you're a little bit on the side, it will roll down to the deepest point in the landscape. This one would roll down here, and one here would roll down in this segment. And in principle, that is what's happening, or actually what we're doing is flooding the landscape. So we are starting from the deepest points and filling up with layers, and so on. And once we have a meeting point, a saddle point between 2 regions, we are starting to building a dam between them. And in the end, you will just have these dam lines, and that is your segmentation. So this one would, as you will see on the next slide, not yet, sorry. So we had a segmentation, we compute a distance map from it, because the distance map is essentially this mountain this mountain landscape that we want to use. In the distance map, we can find some local maxima. So here we have one here, and we have one here. The algorithm I used now to find these maxima also find saddle points. So we got one here, even though it's not really our maximum. And when you let the watershed algorithm run on it, we get pretty nicely a block here, a block here, and a block here, which more or less corresponds to what we want. But this one is an oversegmentation. It was kind of, the algorithm was misled by this saddle point. This part here, I actually don't know where it comes from. Probably if you look into the full image, then you would see, okay, there is also something. But with the segmentation we have done in the current condition, we don't see this as a structure, actually. So this is something we have to live with in this case. So we can see that one of the components, actually label 2, is too small. And that's actually one thing with the watershed segmentation, that it's very prone to do over-segmentation. So it finds many, many more objects than it should. So we can actually delete unwanted seeds just by identifying the size of them, size of the areas. And you can see here, if we look at area 1 is 82, that's a keep. Area 2 here is 7, so it's less than a given threshold, so don't keep it. And the next one is 59, it's a big one, okay, keep it. And the last one is also larger than the threshold, so that one we also want to keep. If we do look at this cleaned maximum image, you can see that now we get a watershed segmentation, which actually is pretty close to what the ground truth is. Still, the line should maybe be around here, but that is what we get from the structure, so we can't do much more about that. And again, I don't know how the ground truth was defined. So maybe it's a human labeling, and the person who did the labeling maybe had a different idea than this algorithm. And also the quality of how the labeling happens also depends on how good you did your first binarization of the image, and second, how you did your pruning with opening and closing. All that has an effect on how the distance map looks like, and the distance map, of course, guides the watershed. So if you get the wrong distance map, of course you will get on the wrong place. So let's look what we have when we're doing a scale up. So let's run the watershed. You see, there's quite some code to get here. So what we're doing, we are computing. First, we do some segmentation here, opening to get rid of unwanted pixels. Then we have the distance transform here. And we want to locate the peaks, so these local maxima. And then we run the watershed. And after that, it's mainly just visualization. But this part here is the important for doing the watershed. No, actually not the top two, so only here. But anyway, when we run watershed on the image that we have segmented using Otso, we see that there is a lot of objects around here. Some are really split up in very tiny pieces. Even this one is split across, and this one is sliced here. So it's not really what the ground truth looks like. Now we want to get something better. We can also see that, for example, there are even missing cells around here and here. Yeah, a lot of missing cells. The reason why we missed these cells is that Otso didn't manage to find them. So that would be going back to step 1 and find a better segmentation algorithm to identify the cells. that is not that we can't blame Watershed for. But the blame we can put on all these over segmentations that we can see here. There is even a very large amount in this one. So why do we get this over segmentation? One reason is that we have irregular shapes, and misclassified pixels can produce a lot of local maxima in the elevation map. So if you, for example, have a round object like this, the distance map should ideally look like this. Now, if you would have two misclassified pixels, just single pixels, they are very tiny, very innocent. But when you start computing the distance map from this one, it all of a sudden looks like this, which gives us actually one local maximum here and one here. So there would probably be a watershed line between them like this. So that would be a splitting of this object. And also, if you have other shapes, could be that you, I don't know, have something like this, and then there are maybe some notches around here and maybe something in here, then you get a lot of small variations within the object. Even though this is a correct object, it could be that you get one island here and one island here, and then it would be split. This is something that happens, for example, if you have natural grains of some kind in porous media. It's very common that you get some strange shapes of the objects, and every little narrow point will produce a new segment. And you could see it, for example, in one of the cells, which was like this, and it was chopped up in many slices. So probably there were some small details along the edges, and these produced local maxima all along the whole object here. So what we want to do now is, one is clearly finding a better segmentation algorithm. And the second one is to use a different algorithm, a little bit more complicated. And then we can go using a couple of algorithms based on morphological reconstruction by dilation and erosion. These are algorithms I haven't mentioned before, but it's a kind of, in short words, it's an iterative algorithm that reconstructs a mutual minimum or maximum between a mask image and a true image. And that are very helpful algorithms when you want to locate minima, or you want to locate, or you want to put markers on the image. So just to compare an algorithm called Hmax, it is, in principle, what it does is, if you have some kind of landscape like this, you say, then you want to identify local maxima that extends out of the background by more than H gray levels. So we would compare to this line more or less in this case. And here we would have something that is greater than the H. Here is, so this is greater than H. This one is too low, then it wouldn't produce a maximum. So this one would just be forgotten. So what you do when you apply the Hmax, you just say a call. Let's see where we do have it. Here. So I have it over here. So you have your distance map, and you say you want to compute something with the height of 2. Then it locates every place in the image which has local maxima which are higher than 2. If they are too low, then they're not found. So if we compare the peak local max, which also found this saddle point, a saddle point is not really a maximum, a distinct maximum in both directions. So it will not even be found. And that gives us, with Hmax, we get these 3 spots, which was the same thing we actually got when we did the pruning afterwards, but this one gives it to us in one shot. And with that, we can actually already do a thresholding of the size of objects that we want to bring into our watersheding. The other one is an algorithm called min-impose, which uses the reconstruction by erosion. Looks pretty ugly, this thingy here. If you want to look into more about how it works and what it is, I recommend you to look into the book by Pierre Soil, which I'm actually referencing in the starting of this part here now. In principle, what it does is it is like if you have a membrane, that's like something like this, and you have a little minimum, and what the min-impose does, it's like pulling down to get you really strong minima in the image. And this is very useful because then Watershed would start from the same point and everything is like funnels going down to that point. To compare what's happening when you do this is you have the normal distance map. Actually, Watershed wants it flipped, so the maximum becomes minima. That's the way the algorithm is defined. So you always put a minus sign, like here, on the distance map. So the original one only has a very dark point here, but if you use the min-impose, you can see that these points here, they are very black, and also that is much lower contrast. Actually, I think it's just because of the grayscale or the color map resolution that you don't see it here. But anyway, when we run the Watershed with method 1, it looks like this. Method 2 looks like this. No big difference on this level, because this is a kind of a cutout that is well-weighed for the first version. But now if we look at the second case, if we look at them on the larger scale, you can see here now that if we apply the Watershed on the data, you have some misclassifications here. Actually, that one, this is actually probably, and this too, it's probably a color map problem, which brings me to the next question, next thing. But anyway, in general, you can see that this one didn't appear at all here. Also, this very critical case down here, it's also just single objects. Now, the thing with color maps is they can be misleading. Many color maps, the original color maps, they are usually linear. So if you apply a linear color map on a Watershed segmented image, it looks like this. You can see that it gradually goes from one color to the other one, increasing intensity, but you can't really see what's going on. So what we instead would do is to use a discrete color map. So there are this tab 10 or also tab 20, which has 10 or 20 colors. This can be relatively good, but you can see that there are still bands of the same color going through the image. So they are still not really good. So what I would propose is instead to define custom color maps. So these functions I have implemented, one is where we have random colors. And then in this color map, all colors are fully randomized, with the only distinction that I also set a background color. So the largest class, or the 0 class, gets a controlled color. Usually I choose black. Another one is to use the golden ratio on the HSV color space. So in principle, what you do is you go around the the color wheel and always pick up opposite colors. So if you have a color wheel here, starting up here, the golden ratio would give you the next color here, and then the next color here, next color here. So there is a slight shift all the time. And if you look at the color wheel, it's usually you have the greatest contrast with a complete opposite, a direct opposite color. So this gives a very high contrast, really a flip-flop between the colors of two adjacent indexes. So if we look at what the same image now, when I'm using tab 20, random or golden ratio, and you can see that tab 20 to begin with actually starts missing a lot of data up here because they have the same color as the background. With a random, you can really nicely see all separate segments. Also, this block here looked solid, but it's actually very split up. So this is a good tool when you start working with the color maps for for watershed segmented images. In particular, if you have very many items, then it's good to have color maps like this. So now I'm going to round off with a 3D example. When you work in porous media, it's very common to scan grain packings of different kinds. So I was working in soil physics, and we had sand packings of different grain sizes. And in this case, I have two sieved fractions of sand, one fine and one coarse. And the idea was we wanted to investigate what happens at the interface between two fractions of sand. So in this example, our task is to separate the two fractions. And the workflow is first, of course, loading the data. Then we have some image preparation, noise reduction, binarization, clean out misclassified voxels. And after that, we had the watersheding. So computing a distance map, identify the grain peaks and make sure that they are nice, and then apply the watershed. So this is what has been done already to this data when we get it. And here you can see a nice example. We have the bi-level image with all the grains. You can even see for yourself that there are some small grains, there are some larger grains. And after the watershed segmentation, it looks like this. And here I used a random color map. And now we can compute a lot of region properties from the watershed segmented data. So let's just use the region props table function. That is put into a data frame. So we get a nice table to work with. And actually data frames is something I've been using throughout these lectures, but never really put some notice on it. Next week, I'm actually going to give you a little bit more background how to work with data frames, because it's a very powerful tool. So anyway, what we get in this data frame is label, area, and the centroids. Is actually what I'm asking for when I'm looking for the properties. I could ask for more properties, but right now I think it's sufficient to use these. An area in this case is actually the volume. So it's the pixel count of each object. And we can see now that we have the maximum area is, no, minimum area is 1, and the maximum is a lot. While the median is around 12,000. So there is a great span in this data. Looking at it, so we need to prune the table, because otherwise it will be very misleading. And this very huge object is actually the background, which makes sense that it's so big then. So what I'm doing, I'm pruning the foreground, or actually I'm labeling foreground pixels of foreground objects that when the area is less than 10 million, then it's an object. Then I also remove some small objects, could be some misclassifications, I believe, or something at the border. And then we can see that if we look at these, you can see that we have foregrounds is true for most of them, but then we have this big one, which gets false. And then we have the small ones, some are true, some are false. So this table is something we can use to extract or filter the table. And then I just say the grains, they are, if foreground is true and small is false, then I want a copy of that. So now we have extracted our data that we are actually interested in looking at. Now we can look at the what the data looks like in the in this table. We have the volume histogram. You can see that there is some kind of, I don't know, very skewed distribution. So there are not so many large objects, but very many small. We can also look at the centroid distribution. You can see that it's much denser packed up here, down here in this region than in this. That's more sparse. So I believe we can already, from this view, we can already see that there are two fractions. One is large and one is small. Pair plot is something we have been using also many times before. And now it can actually help us to identify which are the features we really want to use in our segmentation. And we can see that label versus centroid 0 doesn't bring much. It's just uniform distribution all over the place. More or less the same for centroid 1. So that are the coordinates in the XY plane. All grains, they are distributed all over, more or less uniformly. So it doesn't give us much information. What, however, gives us information is label versus area. And the other one is also label versus centroid 2, which makes sense. If you remember back on, looking back on the centroid distribution, you could see that there was a little bit, it was sparser in one part and denser in one part. So this is actually what we see, that in both, let's see, in this one, for example, you can see it, that the volume is more compact here than here. So it's actually, with the depth of the object, you can see that there are different sizes. The other one is that the label is usually starting from the top and going down. And that also gives us this very nice distinction in this, we can see about here is the knee that separates the centroid of the large objects and the small objects. Looking at those a little bit more together, we can see all combinations produce some information that is relevant. So why not combine them and see what happens? So let's looking for clusters. Now I'm looking just at label versus centroid. Here in 3 dimensions, I'm looking at label, area, and centroid. You can see that the knee is still visible, but it's spread out a little bit around here. Okay, that's an interesting information to see. And now we want to do this separation of the grains. And let's just run k-means. We have 2 classes, of course, nice. It's clustered, so k-means sounds like a good choice. So I'm running k-means with the grains for area, label, area, and centroid too. And then doing some plotting, but nah, it didn't work really. You can see here that we get the separation line around here. So it's not really separating at this point as we would like it to have. And you can also see that the effect is that we have all classes, both classes mixed up with each other. It doesn't really make sense. The reason is, if we are looking closer to the axis labeling here, you can see that the labels, they span from 0 to 1750. And the centroid spans from 0 to 300, while the area is spanning from 0 to, let's see, 250,000. So there's a huge span. That's why also we get the cut around here, because the area is so dominant in this clustering. So what we need to do now is normalizing the data. And what I'm doing is I'm doing a statistical centering. So I'm just subtracting the average value to center it, and I divide by the standard deviation. And that I'm doing on all objects. And now, after the k-means clustering, we can see we got the cut exactly where we wanted it. And the other one is we have here, you can see that the grains are actually now, or the grain positions are now nicely separated in a way that we would expect from this data when we look at it from the beginning. Now we can look at the grain histograms and grain size histograms. And actually this also makes pretty much sense, because the larger fraction has a wider distribution than the smaller fraction. Oops, that was not so nice following. But anyway, you can see that and also that the distributions, they should be overlapping. So these histograms, they really make full sense. Now the next thing, now we did some statistics with the histogram, but we want to have a final image which actually masks that we have grain size A and grain size B, or class A and B. And for that, I have, again, I'm using this reconstruction by dilation in order to paint in the classes of each grain into the image, or into a image. And the result of the label assignment comes back here, and we can nicely see, okay, we got small grains up and large grains down, and in both directions, it's pretty good. Apparently, this is a large grain, or was classified as a large grain. Can be discussed if that's correct or not, but anyway, it was classified that way. And also looking at the cut plane, you can see that some small grains are peeking through. So with this, we have now separated our two classes of grain sizes in this image. We can also look at the interface surface. Here I just projected one of the classes. So I just computed the sum of one class only. And then I get this kind of map. So you can see that some grains, they are going through into the other class. So it's a little bit deeper, but otherwise you can see that it's relatively homogeneous, around 100-ish, somewhere around here. So that gives us the height of the interface in average. And with that, I come to the end of today's lecture. So we have been talking about skeletons to analyze thin structures. Ways to prune these skeletons are important because of noise that produces spurious branches. And also what we can do with this skeleton is to doing analysis of the topology, because the topology is preserved within the skeleton, in principle, you should be able to reconstruct the object that it represents. If you really can, is the question, but in principle, you should be able to. Then when we look at grain samples or item samples, then watershed segmentation is very helpful to work with touching grains, because that is something that component labeling wasn't able to handle. And the problem with watershed is that it's very much over-segmenting unless you guide it very well. And it's a very popular and frequently used algorithm. You find it in essentially any image processing toolbox or an image analysis tool. So it's a very popular one. There are, of course, other algorithms for doing this, which I'm not going to mention during this class, but there would be, for example, there is one called random walker, which computes a probability map for different items, and from that probability map you can identify where they are. That one actually also does, at the same time, does the segmentation for you. Another one would be to work with level sets, which is using partial differential equations to identify regions. And so it's like a rubber band function that shrinks around the object. Also works on the grayscale if you like. So these are options that you could possibly look at if you are interested in this kind of segmentation. A last thing before I end and go over to the exercises is it's getting time to think about projects. If you want to do a project, please contact me. I have some proposals, but if you have a project or something you could extract from your master thesis, PhD project, it's probably more useful for you, and we can discuss if you want to do what we want to do. The projects are not giving you any credits in the sense that they are not mandatory, but if you like, you can use the project as base for the discussions during your exam, and that means you have gained some ground because you know what you have done, hopefully. So then I can use that as a starting point. So that is an option that you can use. And otherwise, the project is good because for you, because you get guidance to solve your problems that you may have in your own projects. Yeah, I think that was it for today. And next week, I have shuffled around a little bit in the program. I have moved the statistics lecture to next week instead of doing dynamic experiments. So next week is statistics, data frames, and plotting and visualization will be the topic. So with that, I thank you for today and see you in the exercises.